Guess what time it is? It's Jamie Blake's in the office doing boring paperwork, and he'll explain something to this camera method because he's bored time. Wonder if my pens work. Yeah, let's go! This is all about, at the weekend with the little Heathrow incident as they call it now, I mentioned HV ring mains and HV feeds and that, and people were like, what's a HV ring main? I was immediately like, oh my god, I know what that is, I can explain that in the boring video on Monday. So that's what I'm going to do now. So this is not, I'm not a HV engineer, yeah, but I know what a HV ring main is, enough to explain to you. Don't be one of those people in the YouTube comments going, oh, that's not right. I've been a HV engineer for 14 years and you're doing it wrong. I don't fucking care, you c***. What I'm trying to do here is explain things to people so they have a brief understanding of them, not get in the weeds about the technical details regarding your degree. So if you're one of those people, fuck off. Also, if you're one of those people that goes in the comments and says, oh, it'd be loads better if you didn't swear. Oh, I can't watch this with my children. Fuck off, you fucking c***. It literally says in the fucking description to my fucking YouTube channel that I like swearing and I don't give a fuck about people like you, yeah? Just because you fucking love Jesus and hate swearing don't mean I have to change what I do. I'll just finish off there. There's no legal reason why I can't swear. There's no legal reason why I have to make YouTube videos. So if you don't like how they're made, fuck off. Like, I don't like fucking boy bands or Ed Miliband or fucking Piers Morgan. I wish they'll get the fucking see and die. But unfortunately, I have to put up with them because they're just doing things that are legal. So if they don't like swearing, go and find some other fucking geezer on YouTube who's explaining UK infrastructure without swearing. Because there's fucking no one. Or just get used to it, you fucking melt. The quest for good whiteboard... Just kick the fucking tripod, you cunt. The quest for good whiteboard shots continues, and he's continuing. Anyway, based on my Heathrow video, here's the arrangement of my local substation. So let me go over a few bits in this so I can make these 11 kV ring mains make sense, because where they're fed from is important. We've got a 33 kV supply coming in, and we've got a second 33 kV supply coming in. And as you can see, they come from two separate sources and are not connected on the 11 kV side. There is nothing joining these together. They are separately fed 33 kV incomers. How your area works may vary. They might have a bus section on their side. I don't know. Everything's fucking different. That's important to remember. Then there's two 33 to 11,000 volt transformers which feed the 11,000 volt switchgear. Now, I'm going to talk about the 11,000 volt switchgear and the little oddity on here that you won't recognise, because it's just the same as a fuse board, but it's got something a bit weird going off. So the 11,000 volt I just sat on. Oh, fucking hell. That's just gone on my horse. That was close. That could have been really fucking nasty. I used that to draw the transformers. What a dick. I'll do this again. In the 11,000 volt switchboard, this happens, yeah? Now, let me get rid of this bit I'm calling the bus section here. Let me remove the bus section, because now what you'll see we've got is, we've got a transformer feeding a three-way fuse board. Let's think of it like that, yeah? So we've got a transformer feeding a three-way fuse board, and we've got a transformer feeding a three-way fuse board. And out of that, we take all our supplies to our 11 kV stuff, which we're going to get into. However, it has this bit called a bus section here. And the bus section looks like that as just a switch in the middle. And what you can do is, you can leave the bus section open. Therefore, you've got three circuits and three circuits fed from different transformers. Or, you can connect it together. In which case, you've got all 6 circuits being fed, sharing the load off both transformers. Now, generally, we keep the bus section open because it keeps the fault current level down. There are ways of keeping it shut, but you have to come up with the clever protection to do that. So we've already stumbled upon a point there, yeah? Remember, don't keep the tripod. Remember that this is 11 kV distribution. Each one of these lines is 3 cables, L1, L2 and L3. What we need to remember here is that unlike our normal fuse boards and distribution at LV, there's a lot more protection going off here. So can we leave the bus section shut? Yes, we can. And have the dual thing, so if one of them blows up. So what you're seeing there is if that one blows up, like that, Heathrow style, What you can work out is, oh, I've missed a bit here, look. I've missed some bits there. There we go. Even I make mistakes. So, if that one blows up, you could open that switch and isolate it, and then it'd be fed from both of those. Now that should make sense now I've drawn it properly. So then, if that one blows up, you could close that one and make a gap there. And the bus section will feed it across to the other side. Let's go through the process, for example, of switching out a transformer for maintenance. So what we'll say is, the bus section's open, look, and that transformer's feeding that side, and that transformer's feeding that side, and the bus section's open. Now let's go through the process of switching this transformer out for maintenance without affecting the supply. First thing we do, and this is simplified, is we close the bus section, so for a temporary period of time, the transformers are feeding all 6 circuits. Then, we open that one there, and then we'd have one on the 33 kV there as well. And now, that transformer is switched there, and you can operate on it for maintenance, whilst feeding it from this one, because both transformers can meet the load on their own. Hope that makes sense. So now at this stage, what we're going to do is, we're going to work on the other transformer. So what we do is, we switch that transformer back on, and we switch that one off, and we switch that one off there, and now this transformer is isolated and safe to work on, while the other transformer feeds the gap. That's the benefit of having the bus section, linking them together, is that you can have uninterrupted supply maintenance and things like that. So that's just how a distribution works. It's a bit like a fuse board, but it's a bit more posher. But we're interested in what happens down here on the rings. Let me show you what the rings do. You're probably wondering how the electricity board managed to maintain the electricity supply to your house for an extremely long period of time without interruptions. And the fact is they don't. Well, they sort of do, but it's not the same supply. It's made possible by this, the HVT. So every transformer near your house that converts the 11,000 volts to 400 volts, 230 volts, will have one of these in. Not this, this is a model, yeah?
These are small, but the ones out there are far away.
This is a HVT, and we're drawing the board how it operates so you'll understand how these work in the rig. Because this enables you to have uninterrupted supplies to your house, no matter what they're doing on their equipment, because they will design all this kind of stuff in. So let me just draw a HVT on the board so you can work that out. And hopefully this time I'll draw it properly. And then I'll demonstrate it on this, and then you'll know what I know, you cunt. Right, here's a drawing of a HVT. It's a unique piece of switchgear manufactured for the very reason to be a T. And what happens is, the bit there, those cables, they're the cables, so I'll remove those, yeah? That's what you get. You get that. So you've got a leg here that's in or out, doesn't really matter. If people call them in and out, it doesn't matter. A leg here that's in and out. Then off that, you've got a piece that comes off there, and the T, there's the T, that goes to the transformer. Now, if you put energy in this end, the transformer will get fed. If you put energy in this end, the transformer will get fed. If you put energy in both ends, and it's synced out and phased out so it doesn't explode, so the electricity can talk to each other, basically, be together, without getting upset like your mum and your dad do. So you can put energy in either side and the transformer will get fed. You need to though, if you was feeding it from both ends, like your mum likes, so say you got a feed in both ends for the example, you could switch that switch off, the transformer doesn't know it's been turned off, it carries on working. Switch that one. I'll re-explain that without all the innuendo so I can get the job done in one go. If you switch that side off, the transformer still gets energy from this side, it doesn't know it's been turned off. Switch that side back on and switch that side off, the transformer now gets energy from the other side, it doesn't know it's been turned off, it doesn't matter. And if you switch them both on, it'll take the supply from both. That's the unique point about a T. It's not very good for drawing, but it just so happens I've made a model of one, aren't I great? Before we get into this, remember that every HV ring main or feeder or whatever will be configured differently. I'm going to go for a very basic one here, which is going to incorporate drawings already done on the board to show a proper ring with a normally open point, which is something we're going to cover in a minute. Here's my little model of a HVT. Let me just take you through this and demonstrate how a HVT works. I'm going to introduce something here called earthing, which is a bit weird, which I have to cover in a separate video. But I have to realise that on HV networks, a thing called earthing exists. And that's when you isolate a piece of cable at both ends of it, you then put it into earth so that any energy stored within it is gone. And it's just how they do it with HV networks, yeah? It could have a video on its own, but this model demonstrates earthing. But more than anything, it demonstrates a HVT. So I'm going to show you how a T works But just bear in mind, there's an earthing feature on here that we're not going to discuss in this video, apart from this bit that we've just done. So we are. What a knob. Here's my HVT. I've tried to make it as true to life as you can without spending fucking hours doing interlocking. Remember, red is energised, live and on. Yeah, green is off and amber is in earth, which I'll have to cover in this bit, yeah? So at the minute, look, you can see the transformer is on. Because if you follow the line, look, this cable is on and this cable is on. Now, if I switch this cable off, it's green, look. The transformer is still on because the supply is coming from here. Yeah? So it's still live. Now, if I switch this on and switch this one off, transformer's still live because it's getting its feed from here. So you can see that on a HVT, you only need to supply it from one side for the transformer to come on. However, if you switch that one off, then that one... What's weird is now is I've switched that one on to make that go green because that one's off. But in reality, that'd still be on. It wouldn't be live, but it'd still be switched on, which is a weird thing to consider, yeah? So the transformer's still switched on and connected to these buzz bars, but both of these cables are dead. So that's how it works. So now the transformer would just be, there'd be no there, you know what I mean? There'd be nothing available. But as we switch this one on, it'd take its feed up that way. And as we switch that one on, it'd take its feed up that way in a ring, within reason. There's loads of other bits and bobs to go with this, yeah? Also, on these units, you can put it into what they call earth. So now I could go from on to off and earth. And what you do is, you go to this substation and you'd switch it off, yeah? Then you go to the other end and switch it off. Then you put it into earth at that end. Then you put it into earth at this end. Then the cable underground will be off and earth. It's an HV thing, don't worry about it. But if you see the amber lights or the earth symbols, that's why it happens. So the clever bit about the T is, like we said, one side can be off. And even in earth, actually. And it will take its feed from the other side. Likewise, it can be that way round. And that's why we have the T's, because this transformer has never been off. And that is why your house doesn't go off. I'm going to cover a HV ring main now. But I'm also going to talk a bit about LV interconnections and things like that to show you why your power never goes off. Whiteboard before... Whiteboard recording is such a dick, yeah? So far I found the best way to do it is to have the tripod high up and point it down, which gets to the reflection of the lights. If anyone knows how to get reflection of lights, if there's a filter or something they can get, let me know. But then again, I just use iPhone, so anyway, I'm going to turn those lights off. Lighting is the worst. Right, back on this HV thing. Hopefully I've left enough shot there to cut myself out in Instagram, in YouTube. I've made a mimic board because, one, no one's going to let me use a real mimic board because they're fucking using it for their HV stuff. Two, I've been waiting 12 months to get a fake, like a knockoff one on Amazon or eBay or whatever. They just don't come up for sale. And I haven't been able to get a redundant site with one on. And no one's going to let me go in a training establishment and show this for free because they want paying or something like that. So I'm actually moving a little bit closer. No, that's right. I need to go out. I'm going to show you what's going off on this. So this is a mimic board. Let's have a look what's going on for the mimic board. If you watch on YouTube, don't watch this on your phone. You probably want to watch this on TV or something like that, so you get my big, beautiful face. Oh yeah, fucking rusty. Oh man. Where we've got a cross, the switch is closed. This is not a schematic proper. On my version, where we've got a cross on yellow, the switch is closed. Where we've got an orange, switched off. And then we've got the blue one, which is the normally open point. I'm going to flip you around and do this because I'll get a better shot with the front-facing camera. So I'll flip you around, I'll take my beautiful face out of shot now. We'll have a look at this HV ring main. Right, I'm using the forward-facing camera now, which is a bit of a problem because I don't get to see where I am. Anyway, I'm not going to be here for much longer. Here's my ring main. And for all the people who say don't do Instagram, yeah, record your videos on YouTube, I like the 1 minute. But anyway, I'll digress. In the situation here, yeah, you'll see everything's closed. That's unrealistic, yeah? Let's open the bus section. But hang on, no. Let's leave it in, yeah? So at the minute, you'll see power come down this transformer or this transformer and get to these buzz bars. Flows across the buzz bars from both transformers. And at the minute, off. And it goes out there, look. Down that ring main unit. All the way through that ring. All the way back there and into the other side of the board. But it doesn't go in or out, but it's live from both sides. That's what we need to understand. So hopefully you're happy with that so far. stand by for oddities. Yeah, it wouldn't be like that. Because one, we wouldn't have the bus section closed. We'd have the bus section open because we wouldn't want double the fault current. 2 times the transformer, double the fault current, yeah? So the bus section, normally operation, would be open. But now you'll see we've created another bus section through the ring main. So what we do is we have a normally open point. So we take a point about halfway, which I'm going to make here, and there we apply a normally open point, and we make that switch off. Now that does something a little bit weird, and what it does is, can you work it out? What it's done is it's made 2 radials. So now there's 2 radials coming out the board. But hang on, it's called a ring main unit. Well, we say ring main unit, it's called a ring main. It's physically wired as a ring main, but it doesn't have to be electrically connected as a ring main. So here we've got a typical ring main. 1, 2, 3, 4 transformers fed from 2 different sides of the board with a normally open point here. So effectively what you will understand it as a normal electrician is, here that comes down there, look, down there, and ends here. That is a radial. And then we've got another radial here, which comes down there, and down there. So now we've gone from having a ring main, although it is wired as a ring main, to having 2 radial circuits. But that is not the point. It's not meant to be a ring main. Now what we're going to do is number the substation so I can show you something. I've numbered all my breakers. I've numbered all my substations. 1, 2, 3, 4. And I've labelled my breakers. 1, A, B, C, D, E, F. If you look around on the network and every substation you come across, you'll see it's got a number and it's got a name. Because when you speak to people out in the field, the name's an easier process to do. I know someone who may be watching this video, his second name is Alan, and he likes jam sandwiches. And there's a substation somewhere called Jam Allen. I think that story's right. He'll probably correct me if it's not. But yeah, on the network, you'll see substations name stuff that's not there anymore. Like you'll see one called, there was one in, it'll be named after an old factory that was on the site. So they show quite a bit of history. It's interesting to see the names and that, so keep an eye out for it. But anyway, so there's a little bit, look, over there on that pole, you can see there is a switch on that pole. I'll get a closer one then and find it later, but I've come to look at this one. It's on the way to work. This one's got a name, look. It's called Oxton Hill Farm 88/car, called Oxton Hill Farm 88/3484, and it's got a load of stuff on there. It's got a little interesting bit on there as well, look. This LV network is non-standard rotation, and it's got a little warning thing on there to say that it's non-standard rotation. Up on the pole, you've got the 11,000 volt cables coming up there in that metal trunking. There they go up there, 3 phases to that pole mounted transformer manufactured by ABB. This is quite a recent addition, because I know, because I drive past it every day. Coming down there, you've got the LV power supplies and the fuses. So down there, there's a set of fuses there, a set of fuses there, and a set of fuses there. And there you go. There's a little bit up there. You've got the 11,000 volt fuses, and if they blow, they hang down. So there's a transition piece there from the cable to the fuses to the transformer, and then your LV fuses down there. Your name on it, your keep off, your barbed wire, all your usual gubbins. I've labelled my substations 1, 2, 3, 4 and my breakers with letters. So what we're going to do now is we're going to have a fault. This is what the ring main enables you to do. At the minute, substation 1, substation 2, which is on this radio, are fed from A. And substation 3 and substation 4 are fed from F. Pause the video and look at that and prove to yourself, because here we've got a normally open point. What we're going to do is, I'm not going to do a fault because that would mean you'd lose the supply. We want to do a cable test on the piece of cable that goes between substation 3 and 4. So we want to work on this section of cable just here. Yeah, in fact I'll put it above here. So we are going to work on this section of cable just here. We might be putting a new ring in, we might be doing some testing on it, whatever. And what we want to do is, we would like to isolate that section of cable so it is dead and safe to work on, but we do not want to cause any loss of supply to anyone on the system. So have a look and think how you might achieve that. So I'm just going to leave a still here and you're going to have a go. There'll be a still here if you are looking But in a minute, I'm going to explain it to you. So now I'll play that elevator music I've got, and you're going to look at it and see how you're going to move stuff around, turn stuff on and off to make it work. Right, first of all, we've got part of this end of the radio, we've got part of this end of the radio. What we're going to do is, we're going to remove the normally open point, and we're going to close that breaker. So now, we have an actual ring. So power is coming from that end, and going to that end. It's energised from both ends. Because of this, we have to make sure that the phases, it's phased out, so you can basically connect, when you connect them together, that L1 goes to L1, L2 goes to L2, L3 goes to L3. That's called phasing out. Now, we have got, everything's live. But if we undo this one like that, and make that off, and we open this one like that, and make that off, you'll see that we have isolated the section of cable we wanted to isolate, and at no point during that process did the power go off to any of the transformers. So watch it again if you have to, but if you look at it, you'll see it never went off. Now, we've done the work on that cable, I'm going to re-energise it back to its normal operating position with a normal open point, but nothing's going to go off. So, we put that one back on. We put that one back on. Then we turn the normally open point back off. And now we're back where we started without any loss of supply or interference to anything. Now it's your turn to do that. I'm going to put a fault on the network. So we're going to have a fault. The fault's going to be there. This cable's going to fault. And what I want you to do is, whilst you're still screen playing the elevator music, is work out what switching you have got to carry out now to sort that fault out. Now, that would have possibly tripped here. I'm not sure this works, but it wouldn't have tripped here. Maybe it would have tripped at the mains. Maybe it would have tripped here. Maybe something would be off. So, but anyway, that cable's gone faulty. I'm not sure how that would exactly pan out in real life. I need to give me advice. I suspect these are switches, and that's natural break. So because that fault, that would go off, I think, and you'd lose all that section. I believe that's how it'd work, but don't quote me on that. But I think that would probably trip, and you'd lose all of this. But that's not the point. What I want you to do is re-energise all the transformers whilst not utilising the piece of cable that's at fault. So I'll leave you a minute to do that. Let's do the answer then. This cable's at fault. That would have probably tripped, causing that to go off because that cable's tripped, and it would have done. That would also be dead. This part, after the normal load point, is on the separate breaks that remain live. So what we have to do is, we'd have to... Oh, now I'm struggling. Now I need to think about it, because this is still on. These people are still on. So we don't want to knock those off. So, interesting. Let me have a think about this. Try and do it. So, this is still on. There's a fault there. We'd identify the fault. So these are off. These are off. We've got to put them to off. Let's try that. Put that off. Yeah, and put that off. I've run out of off, so I'll nick one off there. Put that off. So that section's now off and isolated. Then we'd be able to re-energise that, which would get them on. And then we have to move that normal. The normal point would stay there, but we'd get rid of it temporarily, and we'd put that one on. That's right, innit? Now everyone's got power, and the damaged section is isolated. So that's how the ring main becomes really, really flexible and enables you to switch people on and off or move normal load ports around to cater for faults and maintenance at different times. So what I'll do now is we'll pretend we'll remove the fault and it's been repaired, and we'll put it back to the normal open point, which I think was at transformer 2, weren't it? So This has worked out loads better actually, because you can see with just a whiteboard and some drawing and some post-it notes, I've created a mimic board that you could actually, if you really want to have a play around with this, you can draw your own ring main and you can do it at work or whatever. So the fault's gone. Yeah, the normally open point was there. Everyone's switched on. So we'd switch that on, switch that on, open that, put the normal open point back. Everyone's back on supply. Everything's back how it was. Let's just have a look at one more thing. Let's maintain a transformer so we don't have a Heathrow style instance. So what we do is, we leave the normal open point where it is. We ain't got to worry about any of the ring main. We go to the bus section and we close the bus section, thus temporarily feeding both sides from one transformer. Right then, reshoot. Let's maintain this transformer so we don't have a Heathrow airport style disaster without affecting any of us customers. So first of all, we close the bus section so that both transformers are feeding all these circuits. Then we turn off that transformer there. And we turn off that transformer there. That leaves it on its own. And everything's fed off that side as it was. There you go. That's how flexible a good HV ring main is. I'll just briefly touch on the fact that they don't all look like this. They're not all ring mains. So let's just cover that slightly. So ideally, they'd look like that. And maybe in most towns and cities they do. But it's wild. It's wild, yeah? For a start, one of these might just feed a load of overhead pylons that just feed 3 or 4 farm transformers on a pole. You'll see it out in the countryside like I do where I live. That might come out of there like that, and it might just tee off and tee off again. And at the end of that, you'll have little random transformers feeding little farms up poles, yeah? So be aware you could get madness like that. Another thing to think of is, if this is a small town that's located about here, and there's another small town that's located about here, and this is the main substation of that town, there is a good chance the HV systems interlink, so you can feed one from the other. And then, to make it even more wild, on the LV sides down here, which I'll do in blue, it's highlighted that LV supplies can connect to other LV supplies in something they called LV linking boxes. Just having to walk up my road then, and as we walk up here, we'll find this, look. That is an LV link box, look. Electricity supply. So in there, there'll be some bars that can be moved and short out. Because up there somewhere, there's a substation. And down there somewhere, I know there's a substation. And I don't know where the one up there is, but that will link between the two substations. So if you want to take a whole substation off, you can link that out and do it. Ideally at a quiet time of the day. And like I said, I'll put a picture up now with the inside of one of them, but that is an LV link box. And that's probably been there, looks like, I don't know, a long time. The cable down is lead, pilk. So getting on for, I don't know, 78 years. Someone will tell me in the comments, because someone will know the exact date from that lid. So yeah, LV linking boxes connect one substation to another, so you can do this kind of bus section thing, but you can basically go to this LV linking box, connect the LV out, and then turn a transformer off, so that feeds all the LV sides. You'll have seen these before, because these love exploding in the street and causing fireballs because they are fucking rowdy.
Oh my God.
You can spot them in the ground because they'll often have a concrete lid on that says LV linking box. I personally don't stop enough to see them, but it's wild. So I did a very basic ring, which you will recognise as a ring main. However, I haven't got access to network drawings, proper ones, but there are LV link boxes, there are bus sections on 11 kV, there are bus sections on 33 kV. There's all this intertwined, interlinked switching that goes off. Someone like this on our farm, if that cable goes down, they're fucked. They're going to have to fix that cable and put generators on. In a town, though, you're going to have LV link boxes and stuff everywhere, and the guy who's switching, the SAP, will come up with clever schemes to stop people's power going off. The systems and LV networks, the 11 kV network, the 33 kV network, everything below 132, which is handled by the DNO, your local electricity board basically, is inherently interconnected. They'll also keep a massive fleet of generators for people like this when this goes down, but the in-town stuff is interlinked up hugely, and they will normally keep you on supply. That's why your electricity didn't go off very much. It does get wild though, and without access to network joints, it's very hard to explain, but the ring exists, the radial exists, teeing off it exists. It's wild. So yeah, that one was just the HV ring, but maybe I'll try and come up with a way of explaining the other things than that. But when you're out in the sticks, especially where I am, look at the pylons and stuff. You can see where they go on Google Earth and open them, suck them up, and you can see how little farms are fed. So if you want to have a look at some of them, dive out into the countryside and have a look around there and see how it's all laid out. But yeah, there's a lot of resilience into it, which has the fact that why the fuck did Heathrow go off?